Well, good morning, everyone. Uh, Thank you for joining us for this presentation today on how you can take your simulation to the next level for product design, development, and failure assessment. My name is Devrat Rathore, and I'm an engineering analyst for YS based in Houston, Texas. I work with a team catering to specialist industries in marine and offshore and biomedical. As we go through the presentation, I would ask that you please hold your questions till the very end. You should see a question and answer tab on your webinar screen. So feel free to put in your questions over there, and we'll get to them at the very end. So agenda for today is we'll start with a quick overview of YS, who are we and what we do. We'll also provide a brief update on Simulia portfolio for those of you who are not familiar with what Simulia is. It's an offering by Dassault Systems. Then we'll go to our first example, that is a design optimization of the robotic arm, followed by design optimization for a medical stent. And we'll then get to the closing remarks and the Q&A. So YS is the Dassault Systems software reseller and a platinum partner. We provide solutions for CATIA, Simulia, Delmia, and Ovia. We are headquartered here in Houston, Texas, and we have representation across the state. Across stateside, we have specialists for a variety of industries, all of us on staff, and we have a very active and thriving consulting group. We also assist companies with developing automation and customization solutions, and we provide software training across the country. So here are all the tools that are available from Simulia, which is the umbrella under which the shown software exists. Abaqus, as many of you might be familiar with, is the proven FEA solution. It's a market-leading software, and it will be the crux of our discussion today. FE Safe allows users to study fatigue and durability to predict and analyze service life. Eyesight brings process integration and design optimization capabilities. Some of you might be familiar with Minitab and JMP. Eyesight provides the same solutions, but it is an integrated software into all the engineering simulators that we use, including Abaqus and SolidWorks. So it is unique in that it caters to the engineering market. And Tosca enables users to do structural and fluid flow optimizations. So I guess the first question anybody would naturally ask is, what is the value proposition of Abaqus? Why do we want to use Abaqus? Abaqus is very effective in handling nonlinearities. What is a nonlinear or a linear simulation? A linear FEA study simulates reality only when a number of restricting conditions are met. These include that all deflections are infinitesimally small and the stresses and strains induced by loads remain small enough to let that linear relationship exist. However, most, if not all, problems have some form of nonlinearity relation between the forces and displacements. These can be either it could be in contact, these could be in material behavior, or large deformations. So anytime you're using an FEA software and you are expecting an impact of nonlinearity, you should ask whether you are capturing that and are able to replicate the physics of your problem. So let's talk about some of these nonlinearities that we see in our problems. So nonlinear contact is the first differentiator of Abaqus. This means that due to interaction between bodies or constraints, the nature of forces and displacement introduces nonlinearity, which requires an update of the stiffness matrix K. So contact is not only used in large assemblies like the examples that we see here of the crash impact or of the crimping example, but even in a single body, such as the buckling that we see over here. Self-contact is just as important to model along with contact between other parts. And Abaqus gives us the tool to do that really easily. So what we are talking about here is the capability of general contact, wherein Abaqus lets you define a contact property between, or an interface property between two parts or two bodies, and all the contact surfaces that are created as part of the analysis are automatically detected by Abaqus and properties applied on those surfaces and points. So it's very easy to set up, easy on the user, as long as you are capturing or predicting that those surfaces will make contact. So it's a very useful feature that we find when defining contacts. Moving on to the next nonlinearity that we see, most materials that we come across are highly nonlinear. Metals have the linear elastic range beyond which everything becomes nonlinear. Abaqus provides the capability of an extensive list of material models that it is able to implement accurately. Not everything is created or operates within the linear elastic range that we see in steels or aluminum. So being able to replicate rubber or human tissue or paste, that's where Abaqus thrives. And we are able to define damage and failure limits as well to accurately predict failure in a material. Moving on to the final nonlinearity that we see is that of large deformation. A geometric nonlinearity is one in which the structure's stiffness changes as it deforms, and we see that quite a bit in slender structures. So shown here are some simplistic examples that many of you are familiar with. One of the other key differentiators that we see with Abaqus, and which I personally have found to be quite a step above the rest, is the capability to do number one, the load stepping nature. So that is, you are able to break the problem down into smaller bite-sized pieces. This, you could do it to simplify your model development, or you could even do that as shown over here in this flange case to replicate the true nature of application of the loads. So for instance, in this case, we first apply the bolt preload as we would when we're tightening a flange, proceeded with pressure and end cap loading, and finally as the material, as the connection continues its service, you could either see lateral supplementary loads because of a external effect, or you could see thermal loading. So each of these, you could replicate them exactly the way they would occur during their operation. And also, you are able to get snapshots of what's going on between these steps. So if you want to look at how much preload do I have within the gaskets when I tighten the bolts, so you can get all of that between the step itself. One thing which I find very interesting with Abaqus, and most of us these days have some understanding of Python, the scripting language. So whatever Abaqus model that you create is completely convertible into an Python script, and then you can tinker around, change things that you want within the script itself, and even automate it. So for one of our customers who wasn't very familiar with the Abaqus software, we developed this solution where we created a script that did about 400 iterations of a problem, and it provided them the solutions in Excel. So all of that was done with minimal user intervention for the end user. So all of that is, I mean, we believe it's a game changer. So these are some of the differentiators that you want to look at when you're picking your simulation solution. there are solutions in the market that are great, for a quick solution. So you create your CAD and you want to get a quick answer whether your model is effective or your design is effective. So they are great in that sense. But if you want to do a slightly more realistic simulation, or you take advantage of these advanced features, then Abaqus and Simulia is what the way to go. And we look at some of what we can do using this portfolio of products from the two examples. So let's talk about our first example. This is an arm brace mechanism manufactured by Myomo, a Massachusetts-based robotics company. This exoskeleton, so to speak, assists users who have a partial paralysis or weakened muscle function due to a medical condition. The focus of our analysis will be on the gear and pulley mechanism that operates the arm. We will break our analysis down into three distinct areas that we want to investigate. First and foremost, our mechanism needs to work, and we need to be able to spec a motor that will operate the arm. The pulley system design like these can be complex. We want to maintain tension in the belt, but not too much or too little. Durability is of prime importance. And of course, we want to come up with the lightest weight design possible. In this scenario, we'll focus on the gear mechanism, and we'll find out how we can remove material while keeping the design within its safe operating envelope. So these are aspects of the mechanism that could be studied using simulation. There are quite a few other things that you could do, such as an impact testing, or you could do thermal loading or multi-physics simulations. Operation of the wrist is quite a bit of capability that you could do. So this is just one example that we're looking at. All of these simulations can be done before the material is cut. So looking at the three phases of the simulation that we will do based off our three questions that we want to get answered. So we'll start with making sure that we have a good understanding of the realistic physics of the problem with FEA. We will then take a look at exploring the design by changing some parameters. And finally, we'll see where we might be able to do some weight savings on this design. Using FEA for the first stage, we will identify what are the problem areas that the engineers need to pay special attention to. Just give me 1 minute while I transition. So what we've got here is a model already developed, and we're going to briefly go through this and see how you can set up your model and what are some of the key features that we have used. So effectively, we've got the model being developed in CAD, and you can use CAD interfaces that are available within Abaqus. So these are known as associative interfaces. So for instance, this specific assembly was developed entirely in SolidWorks, and initial simulation to qualify the design was done in SolidWorks. But once you come to the more advanced analysis, or you want to capture some of the non-linearities, you want to start looking at what are the software solutions that are available that can easily integrate with your CAD. So using an associative interface, we're able to import the entire assembly into Abaqus seamlessly. Again, there is another feature which allows you to actually update your as and when you update your CAD within SolidWorks or any other CAD software, it gets automatically updated within Abaqus. So you don't need to do any repeated imports. So the focus of our interest over here is the gear and pulley mechanism. So we've got a display group, and we're going to just keep that and hide the rest of the parts test. These are hidden. These have not been deleted from the model. So looking at our components of interest, we've got the rollers, we've got the gear mechanism, and we've got the pulley system. So the first thing that we would want to do is, we talked about material non-linearities. So we have a rubber belt that we want to apply properties to. And all of these properties can be, you either have a test, you have test data that you want to incorporate into the material model, or if you want to use some of the existing models that have been inbuilt into Abaqus, you could do that too. Or what you could do is you could import your test data, pick one of the models that are already present within Abaqus, and actually compare your material behavior within Abaqus to make sure that the material model that you're picking to capture your nonlinear behavior is closely aligns with your test data. So you have all these various options that you could sort of you could take. Additionally, if you have a belt wherein you've got a reinforcement, you have the capability to actually define such a reinforcement, and that's what we are going to do now. So we've got a steel reinforcements that are being placed along the length of the belt. And so you can define specifically what is the thickness of that reinforcement, what is the spacing of it, what is the alignment. So as these are longitudinally, our angles for these would be 0. So you can see that I'm putting the steel properties into that, and just providing some basic geometric definition. So we are able to capture quite a bit of the realistic material property for that. Moving on to interactions, we saw that we discussed the general contact property, and we'll see some of that right now. So what we've got is we've got a friction property. So that's the general contact being defined here. So there's friction between all parts, and that's what we see as part of global property assignment. However, we've also got frictionless surfaces. So we actually define those frictionless surfaces within the we can add these exceptions. So we've got no friction between the pulleys and the belt here. So as you can see, it's very intuitive to move through the entire process step by step. So you probably won't use all the features and all the options that are available, but you can see it's very intuitive as you move step by step. You define the material, you define the interactions, and now we're looking at what are the loads that are being applied. So effectively what we've got is we've got a torque being applied to the center pulley, and then that transmits power into the gear. So we can see that we're applying torque. And another interesting feature that we've got over here is that the torque or the load that you apply need not always be linear. So we've actually got a non-linear nature that we've defined for our torque application. So you can see like this, we've got this nice looking bell curve for the input of the torque into the system. And this could look like anything. If you have transient loads, you could certainly define that as a function as well. So this is just to give you like a flavor of how it is. It's not very difficult to develop the model, and effectively you are able to do that very quickly, and you have a lot of options available to you. And another, one of the most obvious features that simulation softwares offer is use of multiple processors in the GPU. So that's when you're doing a job definition, that's something you can do then. So we've already got a result file ready. What we see in this current view is the result file, which has actually been in which the upper and the forearm are actually present to show the visualization of when the gear and pulley operate, how the arm moves. So you can define your gear envelope. And as I discussed before, that any changes that you make to the system will get updated into Abaqus automatically. You don't actually need to do any re-import of the model. So once we've looked at the global view, another thing that you want to start looking at is that, okay, is the part operating the way we expect it to? So here we have like this nice animation, and we can see that the belt has a fairly realistic nature of the way it would operate. Looking at the von Mises, we see that we need to look at von Mises and you need to compare that to the yield strength of the material. So that's one of the first things we look at. Another thing that we talked about when we were defining our requirements is the ability to spec the motor. So you are able to get history outputs for any of the variables that you want. So what we see over here is a history output coming for the moment, which is effectively the torque, and we've got the angular velocity. And we're able to determine as to what should be the specification of a motor in this case. So you can see we can identify the peaks and the troughs of the output loads that we are getting. So we've also added steel reinforcements to the belt, and we can visualize them here, as we can see. So we've got based on our spacing, we can see the steel reinforcement cables that are part of the belt. One of the more important things that we want to look at, and that will take us further into our optimization, is the strain that is there in the belt. And we see that the belt has quite a high strain of about 52% maximum, and minimum principal strain is actually negative, so that's compressive. And a compressive strain in a belt like this implies that there could be quite a bit of risk to failure and fatigue. So those are things which you want to try and eliminate and get as per our design. So going forward, we are going to try and see whether using parameters of roller distance and belt thickness or belt material properties, how can we optimize our design to operate it the way we want it to within our design envelope. So going back to, so this essentially identifies what are the design variables that you want to look at. So we've got a maximum first principal strain which is too high, and a minimum first principal strain which is too low. So we know that if we change the distance between the rollers, that will affect the tension and potentially any compression in the belt too, which we see we do have. Additionally, the belt thickness or any material properties even in the belt, they could have an impact on the belt's performance. So we develop an optimization scheme that allows us to monitor these strain parameters, and we can enforce a goal requirement. So in some cases, our goal would be to minimize. So in our case here, we've got a goal to minimize the principal strain, the maximum principal strain, and maximize the minimum principal strain. I'm just taking a look at some of the questions that we have. All right, so nothing. No, I guess questions till the very end. Again, if you have any questions, please please hold them till the end of the presentation, and we'll answer them there. So let's look at what, so we know these are the parameters we want to put into an optimization scheme, and that optimization scheme is effectively what eyesight gives us. So we are able to automate all the design changes that we want, and the beauty of the whole model is that you define your problem at the very beginning. You develop your FEA model, you decide what kind of optimization scheme you want. So for instance, in this particular case, we use the full factorial design of experiment. So with no center point and no replication. So with 3 parameters and a high-low, we've got about 27 combinations that we want to look at. So you don't actually need to execute 27 simulations to develop the empirical relation. Eyesight does that for you. But all you need to do with eyesight is you need to have some understanding of statistical technique, like and there's a lot of material available within the help file, and there's a lot of training available out there in the public domain. of what are the optimization features. So the results that we get from eyesight, you can immediately view a table of the output, which shows you the best design as well as other influential designs. You can look at some of the Pareto plots, which gives you a sense of which are the parameters which are most significant to your results, and whether you can do hypothesis testing and determine which if the impact is statistical or is it not. So you've got quite a bit of functionality available within eyesight, and there's a wide variety of plots as you would expect with any statistical software. And once again, all of this integrates right into your simulation solution, so you don't need to actually develop any in most cases you wouldn't need to develop any complex APIs, and for any of the APIs that you do require, we gladly develop those solutions for you. So once you've run it through this optimization, what we see is our strain went from a maximum of 52% to 14%, and there is no more compressive strain. So you can see that there is tangible benefit in using such an optimization scheme. So that was one of the design explorations that you can do for any of your objective that you have. Another optimization that you can undertake is if you have to reduce your weight. So a software solution like Tosca might help us do that. So let's look at some of the design constraints that we have before we start removing weight from this. We have to maintain this slot for this rotation restrictor, which allows the arm to move about the elbow. We need to keep the key slot for the motor to for the power transmission to go through. And finally, we want to maintain a thickness so that the belt sits snugly over the system. So we're going to show you as to what kind of results you can get from a shape optimization in this specific case. So we have the initial design on the left, and what you see over here in the center image is actually the digitally optimized result that you get as a result from your Tosca simulations. And you can see there's quite a bit of you can see that you've actually, these grooves are unaffected because you defined these to be outside of your design envelope, and you can see that there's a trend that is developed. And so you can go back to your CAD solution and you can estimate or you can redesign your pulley or your gear to look like this, and do a quick revalidation and make sure that it is actually meeting your design requirements. So I mean, it's clearly quite evident, but we've got about a 53% weight reduction using something like a shape optimizer. So you don't really have to take guesses as to where your lower strains are. So you should probably punch some material out of there or do any physical lab testing, but actually just let the software decide and come up with a final robust solution. So that was this first study that we had. Looking on to the next study, so what we've got is a stent, which is effectively installed in blood vessels to open up any restriction that might be occurring due to fat depositions. So we've got an image or a representation of a stent over here. What a stent does is it helps in providing a stable conduit for blood flow, and it creates like a frame which prevents the blood vessel from collapsing. Prior to implanting a foreign object into the body, I guess the most question anybody would want to ask is it safe? Is there a failure rate for something like this? Because you certainly don't want to put in anything which has a failure rate. In the medical industry, they're quite particular about that. And everything has a life, so especially if it's under cyclic loading, so you want to ask that how long will this last, i.e. that after how much time do I have to come back, get another surgery, and get it replaced? So simulation can be used to answer these questions. So you can see an example of a workflow that has been used for stent design optimization. You can not only simulate to predict failure in a stent geometry, but you can also parametrically and non-parametrically optimize the stent to increase life. So this workflow starts with the CAD model of the stent, where through the use of Abaqus and FE-Safe, which is the fatigue solution, the fatigue life evaluation is done for the base case. So that's what we see here. Then using eyesight, we can parametrically optimize to improve fatigue life, and then further using Tosca, we can look at localized stress hotspots, and we can see if there's something we can do to eliminate that. So we will talk in brief about all of these in the following slides. So what we talked about initially was the ability to break down your problem into simpler steps, or like in this case, we have the problem exactly the way it would go through in nature. So the stent is installed by crimping and compressing it and inserting it through into the blood vessel. So we take this stent CAD geometry and we create a finite element model and run simulations under the applied loading. The results from the first loading step can actually be seen here, and they highlight where the peak stresses are in the contour plot. And this is of great benefit because you can now move on to your next load application, which is the expansion of the stent. So the stent contains a balloon inside it, which expands it to plastically deform it and hold it in place in the blood vessel. Again, a great feature to be able to break your problem down into steps. So when the balloon expands from the inside and it's installed the stent in place, we then start looking at the final loading condition, which is the blood pressure loading. So as the heart pumps blood, the load is cyclic in nature. So you can see that on the bottom right, that how the stress is induced as time progresses. So the Abaqus analysis is followed by a fatigue evaluation when FE is safe, which will determine the fatigue life of the stent. This information is obviously of interest not just to the designers, but to the doctors and down to even the patient who wants to know how long the stent would last before I need to start looking at getting it replaced. So once you've performed your baseline studies of your FEA and fatigue, you want to start looking at how can I improve my fatigue life, or what are the improvements depending on your design objectives. What other improvements do you want to start looking at? And again, as we discussed, eyesight integrates very well with most of the software such as SolidWorks and Abaqus, and there's very little user intervention that is effectively required after you have set up the model. So over here we've got a workflow and we see that the SolidWorks model is being used and Abaqus simulations are being run to execute the optimization. So a design of experiment sequence in eyesight will automatically modify each parameter and will produce a new CAD file and a new Abaqus result file for each of the simulations that it undertakes. So again, we've got, if you have 3 variables for a full factorial, that's about 27 runs. It need not necessarily be that your runs will actually, your most optimized result will be within those 27, but eyesight will develop the empirical model that will predict what your most optimized solution should look like. So over here we've got a response surface based on that prediction, and in some cases your objective is to minimize, such as this example that we have. In some other examples, your objective could be to maximize or look at a local minima. So you have all these visualizations that you can actually use, and over here you can see that we've got the length and the radius being changed in this one and showing the result of stress. And for this one we've got a thickness and length varied as we look at stress. So that was again a quick flavor of what iSight can do for you, and I personally find great benefit in especially when I'm doing concept studies, and if you want to if you have a lot of, if your design envelope is slightly larger than in a detailed design and you have some flexibility to play around, it's great to be able to use a tool like this to do an FEA simulation once, and you just let iSight figure out what your optimized solution should look like. And we actually use this quite a bit in our consulting work. Once you've got your optimized design, you can use the Tosca shape optimization as seen here to minimize or homogenize the maximum stress values considering all the load cases. What is effectively happening here is that the nodes of the finite element model are moving in or out, as you can see in the clip on the left, to blend the stresses, and you can see how the stresses sort of reduce in their magnitude. So taking a step back and looking at how we have improved our problem, so to speak, what we had was we had a baseline case, an initial design. It could potentially be an older design that you're looking to optimize or modify for a specific patient. You put that into iSight and you do a global optimization, and that gave us an improvement of 8%. And when we're saying improvement, we're talking about fatigue life. And we further took that into Tosca, and we can apply any manufacturing constraints that it should be no thinner than this number, or it should be the transition between two surfaces. You could also put a restriction on that to allow for manufacturing. And once we complete our Tosca local optimization, we have an overall improvement of 14%. And in some cases, 14% could be a defining factor for that product. And I mean, if it means 14% less surgeries in a patient's life, I think anybody would want that. So just to summarize what we've discussed so far today. So I mean, we've seen Abaqus to be, and it's known in the market to be an excellent tool for realistic simulations. You have the capability to capture all these non-linearities that are true, that are found in the nature of a problem, inherent in the nature of the problem. iSight, Tosca, FESAVE, and Python capabilities and integration within with Abaqus and Simulia provide great features. And I personally use iSight and Python very extensively, and they are enablers, certainly. And this is not being an analyst is not it's not an exclusive club. It's very user friendly, and we have significant support resources available. So I personally come from a product design background, and that's what I did for 4 years prior to starting FEA. And I find great satisfaction in being able to take my own designs from concept stage, and now even doing their own analysis. And it's not just simplistic analysis that I do, but I do you can, using Abaqus or any of the other solutions, you can go quite advanced and you can do a lot of optimization schemes. So I hope this gave you an idea of how you can use Abaqus to sort of complement whatever solutions that you already have. There is some degree of involvement required, but then if the physics of the problem requires it, it's a very useful, easy to pick up tool. So we'll take any questions that you have now. If you could please put them in the Q&A box. I've got R.D. Tehrani joining me here. He's the lead FEA specialist that we have here today. Yes. So any questions that you have, and we'll.
So there was a question regarding the explicit code used to model the gear mechanism or not, that yes, explicit engine has been used for that, for sure, because it's faster, and it doesn't have some of the difficulties for the implicit. Actually, it can be done with both, but implicit is more time consuming.
How many days, hours did this project take? So for the FEA itself, it's fairly quick. Once because the CAD and all the modeling was done in SolidWorks, and it was what we got was a very clean model, and you can certainly do this within from in to out. You could do this within 2 days. Eyesight itself, setting up the model, it's very quick. Once you have a clean FEA simulation, all Eyesight does is it takes that FEA simulation, and you create a parameterized model within Eyesight. It takes a few hours to do that, and then you give your runs. The runs themselves, yes, 27 of them. It takes time. That totally depends on your computational resources. What you can sometimes do depending on the criticality of the project. You can use multiple HPCs, or if you're just doing a study for yourself, you can just do it over the weekend. So setting up the model in Eyesight, not very long. If you have a clean CAD, and if you have all the inputs on hand, setting up the FEA model about a day to 2 days, depending on how proficient you are. So the rest of it is computational power.
Exactly.
So another question that we have is, can we use Eyesight or Tosca to optimize a rubber part, since it is a hyperelastic part? So when you're using Eyesight, you actually can. So because Eyesight integrates very well with some of the software solutions like Abaqus and SolidWorks, you are able to read in the parameter that is being defined in that model. So certainly you can do that quite well for the hyperelastic part, or as long as you are able to identify the coefficients that you want to change. Now, if you were using test data, then you have a slightly more complex problem. And that's why what we had was, in this example, there was test data available, and we used an inbuilt model that closely aligned with the test data to do the optimization. Because if you have test data, then you have a lot more variables that define the points within the material model.
Just a second.
So a third question that we have is, can the optimization be done to improve the natural frequency of a system or stress of a component, and not just weight? So handling the so this is in relation to what I believe is Tosca. So yes, for the stress of a component, this can be done, as you saw in our in the previous example, that we actually, instead of doing a shape, instead of doing a weight optimization, we actually did a shape optimization, and we were able to actually eliminate some of the peak stresses that we get. You define like in this problem, we actually define how deep or how much out the node should travel, and then you can get a visualization like this, which tells you that where is your sweet spot. With regards to natural frequency,
yeah, we can define ranges for natural frequencies for each node to see how will be the response of the natural of the part with respect to
The shape optimization is, so the question is the optimization highly dependent on the quality of the mesh? Your shape optimization is dependent on how you build your mesh, certainly, because you need to ensure that you've actually built separate, you've partitioned out sections that you want design constraints on. With regards to quality of the mesh, it effectively what a shape optimizer does is it runs an algorithm in the background, and it significantly depends upon the results from a simulator like Abaqus. So
mesh quality,
the mesh quality will obviously have a impact on just the FEA results by themselves. If you are okay with a crude mesh for an early estimate, then you would be able to execute the optimization. But then the question really is that with a crude mesh, do you really want to optimize? Are you at that stage yet? If you have any questions, please ask us. In case there's something which we need to investigate further, we'll email you. We'll get back to you on that. So feel free to ask us questions, and not just on what we discussed today, but in general, if you have questions on Abaqus capabilities or Simulia capabilities, we'd be happy to answer those as well.
Yeah, we can answer in more details.
Yeah. It's not just restricted to what we saw here today.
Exactly.
If there are no more questions, I'd like to thank everyone who sat through our presentation. If there's something we can assist you with, and if you are looking to purchase any of the software solutions, or if you require any guidance on how to pick your softwares, we'd be happy to answer those as well. We have quite a few technical specialists on staff as well. RD was here answering questions for us today. So, if you have any projects that you want assistance with, please feel free to reach out to us. Also, look at our website and see some of the work that we've done in the past. Once again, thank you for joining, and have a good day.
Have a very good day.